On a encore un exemple à regarder sur l'utilisation de l'intelligence artificielle. Alors,
We've still got another presentation of this AI. We're going to see now what's happening in the lab. So I'd like to welcome Asma Aziez now. She's going to talk about the use of this technology in the NMR spectra. So you've got about 10 minutes to talk about IE, a deep learning application in NMR spectra. Hello, I am responsible for R&D for Evear Extraction. Today, I'm going to talk to you about the application of AI in a very particular context, in a company, in a lab, not really one destined for research, but an industrial lab. It's a very particular application, as you're going to see. This is our company, Evear Extraction. It's a French company in a small village near Angers, in the middle of the fields, as you can see. A family company. It's been around for the last 3 generations. It was the grandfather who wanted to grow artichokes. Then, obviously, this was passed on from father to son. But the son wanted to recycle artichoke offcuts, waste, macerating the leaves and obtaining an extract. And this extract interested the Americans because they wanted to create a pharmaceutical product based on this artichoke extract. And then Monsieur Rousseleau increased the range and looked towards the international world with a large gamut of products. So the 3 main markets that we target are the medical world, health supplements, food supplements, and some additives. The knowledge of the company begins with the protection of plant extracts from the seed right up to the end product. So around the company, in the fields which belong to the company, we grow quite a few plants, principally artichokes. It's our key product. And this artichoke has been assessed clinically. There are clinical properties which have been claimed and vindicated. And we have shown that it helps with the joint inflammation, and people have eaten this product, but it has actually got confirmed effects on the human body in terms of health, and these have been checked and verified. After growth, then, we harvest the plants. Then there is an extraction process with water or with alcohol. It depends on what the client wants or the specifications. These extracts are dried, or we heat them, or we put them in spraying tires in order to transform them into a powder. And this powder is sold to produce health food supplements and additives. We don't produce this. We do the transformation, the process of the plant right up to the dry extract, either, like I say, in the towers or in the ovens. In the company, we have a quality control lab and an R&D section. I have been in charge of the lab since 2021. In this lab, we try to monitor protection from the beginning to the end, ensuring there's complete traceability, and using breakthrough products, top-of-the-range products and equipment. We work with other university labs, depending on the issue. But the main equipment that we have in the lab, well, you can see them. You've got bain-maries for simulating industrial extractors. If you want to analyze samples, we take our examples exactly as if we were in a company. You've got a CCM there, which allows us to identify the plants. The HPNCs, which allowed us to dose the additives or certain ingredients and look at the profile of some extracts. And we've got the GCMS, which has a particular use. We use it for solvent residue and also for some contaminants or alkaloids, etc. And our favorite is the RMLs. This is the RMN, the NMR machine. This is our baby. In the context, the current context, this NMR has, what does it do? Well, it looks at the metabolic structure of extract. It looks at all the composition, all the molecules, and the molecular point. If it's superior to 1,500 daltons, you can go and look at it through this machine. And this allows us to look at metabolism of each extract, of each plant. For some uses, we can quantify the metabolites, and sometimes we can look at the breakdown of the structure when we look at the molecules if we don't necessarily know the structure. And with the NMR, we can break them down. It's used to control the products and also to see if occasionally we have clients who have very specific demands to look at the composition of their own product in order to offer an equivalent product. This was bought in 2017, and we bought further spectra. So we have databases which with spectra which are experimental, 60 plants, 180 products, different products. Excuse me. So it's constantly changing.
An example of the use of this NMR is a study we carried out with the INRA in Bordeaux on the authenticity of food-based supplements based on acerola. We used the NMR spectrum, and we used dried samples. And what we could do is to dedicate the metabolomic profile per area. We have the aliphatic area, all the amino acids, organic product compounds, carbohydrates, and we can see everything that's aromatic and specific metabolites. If we have an HPLC analysis on acerola, we usually look at the presence of ascorbic acid. If we carry out an HPLC analysis, we look for the ascorbic acid. We have a dosage calculated, but we can't know if this comes from the acerola itself or if it's an additive. Whereas with the NMR profile, we can even see further into detail. So we have a full profile enabling us to really see if there is acerola-based acid in it. Here I have an example of a concentrated powder without added ascorbic acid, and another one with you can see in the aliphatic and the aromatic spectrum, it's different, and it shows that you don't have metabolites that should be present in the acerola. So it shows that in our product there is acerola, and in the other one it's an additive, added ascorbic acid. If you check powders or concentrated products, we actually have defined major markers for acerola. The ratio of ascorbic acid and choline actually was defined. We set the ratio at 2, showing that the ascorbic acid is from natural origins, so the product is authentic. If the ratio is over 2, let's say 20, for instance, it means that there was an addition of ascorbic acid, and therefore it's not a natural occurring ascorbic acid from the acerola, but an additive. So NMR remains a very powerful tool. The only issue is that if we have to record the spectrum every single time for each extract, we have to do a handmade analysis. There will be an experimenter bias effect because we record a lot of spectra. So we need to automate this process. So we decided to look at the literature on AI applications on NMR. Looking at previous works and studies, we could find that the processing of the signal, because an NMR signal is a growth signal in time, there is a Fourier transformation from time to frequency ratio to find the peaks, and some tools can automate this transformation. Some other tools make it possible to have a structural elucidation. So you put in a spectrum, and you end up with a scoring at the end, and the higher the score, the more chance there is that the profile is close to the model. And we have also AI-generated noise cancelling. And so we can also analyze very complex spectra. Still, the analysis remains an issue. So we decided to work on 16 issues to create an automated classification of spectra. And this model, through this NMR spectrum, can enable us to classify our results without using handmade ratios and observation. So we had to find key metabolites for each extract to quantify them and maybe detect addition, such as I proved with the ascorbic acid, and it will be automatically spotted. We started with a model of random forest. It was an intern that came up with this. They worked on our data, part of our data, with a random forest model. To keep it simple, imagine a forest with a lot of trees. We may wonder the solubility of a given molecule. Each tree will vote soluble or insoluble. And we count the votes, and the majority vote will come up with an answer. Here, trees will respond based on the information we feed them in the model. So what we used was our own database, mainly based on acerola products, because we have a wide range of acerola-based products. So we took our own database, we cleaned it up to make sure that the preparing of samples was done in the same conditions, that all parameters for the analysis of spectra was the same, that all the data was clean, and we ended up with 2,000 clean spectra. And we trained our model based on this. So our database was divided in three: one for the training process, one for the validation, and one for the for testing. So we processed all the data, and then we tested our model. If the majority vote classified the spectra in a given classification, let's say the Y class, for instance, well, then this model was assessed based on several parameters: the depth of the trees, the number of trees, the time needed for training. These are specific parameters for this random forest model. The model was trained several times. Its performance were assessed, and then we created a confusion matrix to check the performance and validity of the conclusion. You can see on this validation test, a majority of the spectra were classified properly, accurately, with 100%. There was a small margin of error in some spectra. When looking at them, it was justified. I mean, there was real doubt. There was really an issue on the spectrum which made it classified differently. I just want to say that on the various acerola classifications, with just with human eye, it's difficult to classify, very difficult. We also worked with the University of Lyon. We used another neural network, and we didn't use spectrum in CSV format, but we had a training done with a reduction of dimension. The pictures were reduced, and our model just tried to keep the images where, or the part of the images where there was a lot of information, relevant information. The image was then turned into a it was vectorized, and through a last analysis, and then the classification came out. The model was assessed based on specific parameters for this exact model. And then we created a confusion matrix. And on the confusion matrix, we can see that the classification was more or less accurate in most cases. From these preliminary results, we decided to hire a PhD student to work on this exact issue. And he looked at the issue at a broader level. The point of his thesis is to refine automated classification models by using other approaches and to create an automated assessment of metabolites. He has preliminary results because he started with mathematical models. I will not go into detail. I will shift to perspectives. The point of our project is to start with our products, extractions from plant, into our end products, then with an expertise. So we put through our model with our own database, because commercial databases of plant extracts do not exist. So we are creating our own database. And at the end, we want a classification, a detection of adulterations, an automated identification of the metabolites, and a quantification of metabolites. So thank you for your attention. I would like to thank the various teams from Lyon that worked with us and our own Evear teams. Thank you very, very much, and thank you for the invitation. Thank you, Esma, for this presentation and the illustration of another use of AI for automated processing of lab analysis. We're ready to conclude. I would like to thank our three presenters and all the people who came to present before that.